As we continue on the subject of soil pH, let's consider the factors that affect pH and lead to, for example, soil acidification. Since hydrogen ions can occupy cation exchange sites on both clays and organic matter, when the pH of the soil is decreased, the increased level of hydrogen ions displaces cations such as potassium and magnesium into the soil solution. They can then be leached from the soil. Forms of iron such as ferrous Fe2+ and ferric Fe3+ ions are almost insoluble in soil solutions with basic pH. Therefore, they remain associated with cation exchange sites or linked with insoluble soil compounds. pH can also lead to the irreversible loss of some plant nutrients by promoting chemical reactions with other soil constituents. For instance, at low pH, phosphates form insoluble salts with iron, aluminum, and manganese ions, or can be bound irreversibly to hydrous oxide clays containing these elements in their crystalline lattices. At high pH, phosphates combine with calcium ions in the soil solution to form insoluble calcium phosphate. Below pH 5, the concentration of hydrogen ions is high enough to promote exchanges with the aluminum ions that, in more neutral soils, are rather tightly held at cation exchange sites. In addition, aluminum hydroxides in the clay structure can be solubilized at low pH, releasing further free aluminum ions into the soil solution. Aluminum and aluminum hydroxide ions are toxic to most plants. Aluminum stops cell division in the root meristem and decreases the plant's ability to take up nutrients and water. There is evidence to suggest that aluminum toxicity affects plants to some degree on 30 to 40% of the world's arable land. Acidic soils are particularly problematic in areas plagued by acid rain or in the tropics, where soils are inherently less fertile and acidity levels are increased as a result of deforestation. Naturally acidic soils are typically derived from acidic parent materials such as granites, sandstones, or shales. However, acidity levels in soils can be altered over time by a variety of factors. High pH is maintained by basic cations such as calcium, magnesium, and potassium. The leaching of these cations allow both the cation exchange sites and the soil solution to be dominated by hydrogen ions. Removal of these cations as they are taken up as nutrients by plants and other soil organisms causes similar effects on soil pH. Plants and microflora also increased acidity of the soil solution through the process of respiration. The carbon dioxide released by these organisms chemically reacts with soil water to form a hydrogen cation and a bicarbonate anion. Human activities also stimulate the formation of acid soils. Acid rain is one result of gaseous industrial wastes and air pollution from automobile exhaust. As rain falls, atmospheric sulfur dioxide and nitrogen oxides combine with water to form dissolved or ionized sulfuric and nitric acids. The resulting acid rainwater, that is rainwater at pH 5 or less, increases soil acidity as it becomes part of the soil solution. Cropping systems which remove basic cations tend to increase soil acidity. This is especially damaging in countries that export crops but cannot afford to replenish soil nutrients. Central America and South America have net loss of nutrients through their crop exports, whereas Europe and Asia have a net gain in nutrients. The use of ammonia-based fertilizers, a common practice in developed countries, also increases soil acidity. During incorporation, an ammonium ion is converted into free ammonia as it traverses the root cell membrane, and the remaining hydrogen ion is left in the soil solution, forming sulfuric acid and acidifying the surrounding area. Liquid ammonia is a cheap and effective fertilizer that has been widely used in the U.S. Corn Belt. Since there is no anion associated with it, it does not have the soil acidifying properties of ammonium salts. Some common ornamental and crop plants, particularly in the heath family, the Ericaceae, rhododendrons, azaleas, heath blueberries, are acid-loving, but most plants perform best when the soil pH is between 6 and 7. When soils become too acidic, liming agents such as calcium or magnesium carbonates, oxides, and or hydroxides can be added to correct the problem. The amount of liming agent needed to raise the soil solution to a target pH is called the lime requirement. The pH of the soil solution represents the active acidity, those hydrogen ions currently in solution, but is not a guide to liming requirement because soil has potential acidity. Partly this results from the bound hydrogen ions on soil particles. In addition, when lime is added to clay soils, aluminum ions are displaced from exchange sites. The aluminum ions react with water to form aluminum hydroxide and hydrogen ions, re-establishing the acidity of the soil solution. Eventually, enough lime can be added to overcome this buffering capacity. An additional added lime will cause the pH to rise. The successful addition of lime will relieve aluminum toxicity, improve the availability of phosphorus and micronutrients, increase the activity of beneficial soil organisms, and inhibit some soil pathogens, as well as provide and improve soil structure. Liming of soil is common in home vegetable gardens for areas with somewhat acidic soils. High soil pH is fairly common in urban areas because of leaching of lime from concrete. This leads to nutrient deficiencies in some plants because of the immobilization of iron and manganese. Also, pH must be lowered in order to grow plants such as rhododendrons in alkaline soils. These can be done with acidulants such as aluminum sulfate, sulfuric acid, or elemental sulfur. However, it can be difficult and expensive to neutralize the entire soil, so acidulation is usually targeted only for the soil fraction in the plant root zone, especially in basic, highly buffered calcareous, that is calcium-containing soils. The soil tends to revert to its normal alkaline condition, and continued use of minerals for acidulation may give rise to other conditions that adversely affect plant growth. The effect of pH on nutrient availability in organic field soils, potting soils, or soilless mixes can be quite different from that found in typical mineral soils. In organic field soils, muck soils containing 30% or more organic matter, the best window of nutrient availability is from pH 5.5 to 5.8. The chemistry of these soils and the properties of exchange sites are very different from those of mineral soils. In soil-less potting mixes, most of the cation exchange sites are on the peat moss or composted bark components. Nutrients tend to be most available in these mixes from pH 5.2 to 5.5. So we've seen that soil chemistry is a very complex yet very important part of understanding soil function. Let's look now at some of the key points that we've addressed through this unit. Potassium, calcium, and magnesium ions are major plant nutrients that occur as positively charged ions. They can be held on negatively charged groups, on particles of mineral and organic matter, and released relatively easily for uptake by the plant. Nitrogen, phosphorus, and sulfur are other major nutrients that are mostly bound up in living and dead organisms in the soil. Their availability depends on the recycling activity of bacteria and fungi. Because they occur in solution as anions, they are not bound to soil particles, and they can be leached from the soil more readily than the cations. Now, plant micronutrients include boron, chlorine, copper, iron, manganese, molybdenum, and zinc. Although they are only required in trace quantity, they may be unavailable in some soils and cause deficiency symptoms in plants. Some of the pore space of the soil is occupied by the soil atmosphere, which contains less oxygen and more carbon dioxide than the atmosphere above the soil. Plant roots and other soil organisms need the oxygen in the soil atmosphere for normal respiration. In waterlogged or compacted soils, oxygen may become limiting and carbon dioxide may build up to toxic levels. So you have seen then that many chemical issues or features of soils are important, and we must understand these as we utilize soils either in crop production or for landscape manipulations, be they in playing fields, golf courses, or various gardens. But let's consider then some questions that might be worth for review, and you may use this just for your own study, such as what are soil colloids and why they're important, why are soils with a high cation exchange capacity considered to be more fertile than soils with a low CEC? What is humus? What are the essential elements required for plant growth? Why is change in the pH of soil not permanent and is often required on a regular basis for some soils? Why do some trees such as pin oak, sweet gum, and red maple exhibit chlorosis in the typical alkaline soils of central Ohio? So as you look back on this unit, think about these questions and try to assimilate all of the general information about chemical properties of soil.